When I first talked about the quantum harmonic oscillator, I said there were two solution methods. We're now going to do the analytic solution. We'll start by preparing the Schrodinger equation to simplify it a little bit. Then we'll solve the asymptotic version of the Schrodinger equation, that is, where x goes to very large values. Then we'll solve the part where x is not very large with the polynomial solution. And then finally find the coefficient recursion relation for the polynomial solution. So we start with the Schrodinger equation. E psi is equal to minus h bar squared over 2m d squared psi dx squared plus 1/2 m omega squared x squared psi. We're going to make a substitution of variables here. We're going to replace x by xi, xi being a reduced value of x, which is equal to the square root of m omega over h bar times x. So dxi is equal to this times dx. We now can replace the dx squared and the x squared. When we replace the dx squared in the denominator, we get this squared in front. So we get minus h bar squared over 2m, m omega over h bar, d squared psi dxi squared. And when we replace the x squared in this term, we'll get 1 over this squared. And so we have for this 1/2 m omega squared, h bar over m omega, c squared psi. If you look carefully, you'll see that both these reduce to the same prefactor. The m cancels here, one of the h bars cancel, and I have h bar omega over 2. And here I cancel one of the omegas, and I cancel the m, and I get h bar omega over 2 also. So we can factor that out. If we factor out minus h bar omega over 2, we get this. Minus h bar omega over 2 on the outside. Then we have the quantity d squared psi dxc squared minus c squared psi. If I now divide by minus h bar omega over 2, bring this by itself on one side of the equation, and bring this to the other side, I will get the following with the energy. So we have d squared psi dxc squared is equal to c squared minus 2e over h bar omega. And this then is applied to psi. Now I'll make one more substitution, and that is I'll replace this with a constant that I'll call k. So now I have d squared psi dxc squared is equal to c squared minus k, all applied to psi. So we can solve this using the asymptotic method. We'll first solve for the asymptotic solution, and then we'll solve for the solution close to 0. So as c goes to plus or minus infinity, then this term here dominates the k, because k is just a constant. And so we can rewrite this as an approximate differential equation that looks like this. D squared psi dxc squared is approximately equal to c squared psi. And that's the equation we want to solve at large values of c. So the approximate solution to this approximate equation can be written like this. Psi is equal to approximately a e to the minus c squared over 2 plus b e to the plus c squared over 2. And we can show that this solves this equation approximately by taking the derivatives and substituting back in. So we'll take the first derivative. That gives us minus a c e to the minus c squared over 2 plus b c e to the plus c squared over 2. We take the second derivative, and we'll get two terms for each of these. So we'll get a, and then we'll pull down another c minus c, so that gives us c squared. If we take the derivative of the exponential, if we take the derivative of this, we get a minus 1. So we have minus 1 times e to the minus c squared over 2. The second term is b times c squared plus 1, because there's no minus signs up here, e to the plus c squared over 2. So now I take this, put it back in here, and see what it looks like. So I can realize this by, again, realizing that c squared is going to be very large in the asymptotic regime. In the asymptotic regime, this dominates the 1, this dominates the 1, and so we can approximate this second derivative with just the c squared times this term here. And so the second derivative of psi with respect to c squared is approximately equal to a c squared e to the minus c squared over 2 plus b c squared e to the plus c squared over 2. But it's approximately equal because we had to make another approximation. But if you look at this, this is simply approximately equal to c squared times a e to the minus c squared over 2 plus b e to the plus c squared over 2, but that's just psi rather. And so this is approximately equal to c squared psi, which is exactly the solution that we want. Now, again, admittedly, this is all approximate. We had to make an approximation for the differential equation, and we had to make an approximation here when we take the derivative, but it does solve it approximately. So what this tells us is this is a solution out at infinity, and it makes sense. And so the solution for all space out at infinity is approximately equal to this. A e to the minus c squared over 2 plus b e to the plus c squared over 2. But clearly, this term is non-physical because this goes to infinity at the large values, and we need our functions to be bounded and integrable, so b has to be set to 0. And so our solution at large values of c is just a e to the minus c squared over 2. So now we want to get a solution for all space, because so far we only have the solution at large values of c. So at small values of c, let's assume that the solution is separable. In this case, separable means that we have two multiplied together functions for the solution, but they have the same variables. And we're going to assume a function h of c times e to the minus c squared over 2. So we know that at large values of c, this will dominate and it'll take care of everything, because we know this solves it approximately. At infinity, everything works fine. We are now left with the task of finding a proper value for this function, the proper function that will solve the actual differential equation. So again, we'll take derivatives, and we'll take c dc d psi dc is equal to minus dh dc, dh dc minus ch e to the minus c squared over 2. And now when we take the derivative of this, we have to take first the derivative of this term and then the derivative of this. This gives us a lot of terms. So we'll start by taking the derivative of the stuff in parentheses. That gives us d squared h dc squared minus c times dh dc minus h, all times the exponential e to the minus c squared over 2. When we take the derivative of this and multiply it times this, we get dh dc minus ch times minus c e to the minus c squared over 2. If we now realize that this term and this term will add together, because the minus c comes in and makes them add, and then we have a c squared times h and a minus 1 times h. So we can rewrite this in a more compact form. This follows. D squared h dc squared minus 2c dh dc plus c squared minus 1 all times h, everything times the exponential e to the minus c squared over 2. So this is the second derivative, and now we have to put this in to the full Schrodinger equation, which is the original simplified one. So remember, it was c squared minus k applied to psi is equal to d squared psi dc squared. Well, we know what this is, and this is just already there. So we can rewrite this, putting in psi as h e to the minus c squared over 2 times c squared minus k. And over here we have our derivatives, and this is the function that we care about. Now again, we look at this really hard, and we see that this term, the exponentials cancel because they're on both sides. Furthermore, we see that this term here with the c squared times h is also over here with the c squared times h. And so these terms also cancel. So we can get rid of all these terms, and then we have to rearrange this by bringing the minus kh over to the right side and make it plus kh. And so we're left with 0 is equal to d squared h dc squared minus 2c dh dc plus k minus 1 times h. And that's the equation for h, the function h that we haven't yet determined. We're going to assume it's a polynomial. It's a very general form, and it's a form that can give us some oscillatory behavior, which is what we care about. Because we know that as the wave functions go higher in quantum number n, they have to have more and more nodes, so you have to have an oscillatory type function, and polynomials can do that. We're going to assume that h of c is equal to a sub 0 plus a sub 1c plus a sub 2c squared, and so on. And we can write that as a sum from j equals 0 to infinity of a sub j c to the jth power. Clearly, for the 0 term, we get a sub 0 because this is 1. For the a sub 1 term, we get a sub 1 c to the first power, and so on. We can now take this proposed solution and substitute it back into the reduced differential equation, or the equation for h, and solve. And so we're going to start looking at all these derivatives, because what we need is we need the second derivative and we need this first derivative of h as well as h itself. So we start with h, and we'll rewrite this as the sum that we had before from j equals 0 to infinity. And then we'll write down the first derivative, that is d by dc of h is equal to a sub 1 plus a sub 2 times c times 2 plus 3a3 c2, c to the second power, and so on. Now, we could write this as a sum starting from j equals 1 to infinity, but that's not going to be convenient. We really want to have the sum start at j equals 0, because then we can group them all together later on. And so I'm going to propose a sum that I'll show has the right form. And the proposed sum that I show has a sum from j equals 0 to infinity of j times a sub j times c to the j minus 1. So let's look at the j equals 0 term. So when j equals 0, this term vanishes. And in fact, there is no a sub 0 term. That's good. When j equals 1, I get 1 times a to the a sub 1 times c to the 0th power. And that's perfectly good too, because I just get a sub 1. When I have j equals 2, then I have 2 times a sub 2 times c to the 2 minus 1, which is c, and that's exactly what I get here. And so this works out very nicely, and it has the same limits as the other function. The second derivative is d squared c by c squared of h is 2a sub 2 plus 2 times 3 times a sub 3c plus 3 times 4 times a sub 4c squared. And again, I want to start with the sum that starts at 0. And so this time I'm going to do something slightly differently. Notice that every term except the first one has two factors multiplied times it. The first one, which is from the first derivative, and the second, which is from the second derivative. This is from the first time you take the derivative. This is from the second time. Well, clearly, when I take the second derivative, I could have put a 1 here. So it's a 1 times 2 times a sub 2. That would have made it more clean. But once I realize that, I can simply write this as 2 that depend on whatever index j is. Now, if it started j equals 0, it's convenient to write it this way, and I'll show you how that works. I'm going to have the sum from j equals 0 to infinity of j plus 1 times j plus 2 times a sub j plus 2 c to the jth power. So, for j equals 0, I have j plus 1, which is 1, j plus 2, which is 2, a sub 2 times c to the 0th power. That works. For j equals 1, I'll have 2 times 3 times a sub 3 times c to the first power, which is exactly right, and so on. It all works out very nicely. And so what I managed to do is put them all with sums that go over the same range of indices. But we have slightly different powers of c here. So if I put this back into the differential equation that we had for h, which is 0 is equal to d squared h dc squared minus 2c dh dc plus k minus 1 times h, we have the first term goes from here, and now we can pull out the sums because they're all over the same values. And so I have j plus 1 times j plus 2 times a sub j plus 2, and then I have c to the jth power, which I pull out. The second one, remember, it was c to the j minus 1th power, but this is multiplied times c. So very cleverly, we also have, when we pull this into the sum, c to the jth power. So we can factor that out. When we do that, we get 2 from here times j times a sub j from here, c to the jth power. And then we have k minus 1 times h, but h already has the right power. So this is k minus 1 times a sub j, all times c to the jth power. And so this is the equation that must equal 0. Now, in order for this equation to equal 0, it means that all the coefficients of c, of the various powers of c, must be 0 also, because there's no way to subtract them because they have different powers of c. So the coefficient of each power of c must vanish for there to be a solution to this equation that holds. But fortunately, there's enough minus signs in here that we should be able to get it. So this says that in general, 0 is equal to j plus 1 times j plus 2 times a sub j plus 2 minus 2j a sub j plus k minus 1 times a sub j. That has to be equal to 0. Well, I can group the a sub j's, and I'm going to get j plus 1 times j plus 2 times a sub j plus 2 plus k minus 1 minus 2j a sub j. And that means I can solve for a sub j plus 2 in terms of a sub j. So, if I know the a sub j, I can get a sub j plus 2, then I can put a sub j plus 2 in here and get a sub j plus 4. And this recursion relation is very useful because I can generate all the coefficients starting from the beginning. So I need one coefficient to generate all the even ones, one coefficient to generate all the odd ones. So we have the a sub j plus 2 is 2j plus 1 minus k divided by j plus 1 times j plus 2 all times a sub j. So this defines the even and odd coefficients separately, because if I start with this being even, like 0, I get all even coefficients. If I start with it at equal to 1, I get all the odd coefficients, and they don't intermix. So now we can assume values for a sub 0 and a sub 1 and generate all the odd and even sequences. So this is my recursion relation. And if I want a sub 2, I substitute 0 in here. And so I get 1 minus k over 1 times 2. So it's 1 minus k over 2 a sub 0. If I then want a sub 4, I'll plug in a sub 2 and j equals 2 here. This gives me 4 plus 1, which is 5 minus k, over 3 times 4, which is 12, times a sub 2. Then I can substitute this for a sub 2, and I get 5 minus k times 1 minus k over 24 times a sub 0. So everything can be in terms of a sub 0 for all the even coefficients. Similarly, for the odd coefficients, I start with j equals 1, and I have 3 minus k over 6. And then here, from a3 to a5, I get 7 minus k over 20. Plug it both in, and I get 7 minus k times 3 minus k over 120 times a sub 1. And so the full solution then is given by the sum of the odd and even parts, because the full polynomial has to have all the terms. And we can say then that h is equal to h even plus h odd. And H even has all the even coefficients and powers, and H odd has all the odd coefficients and powers.